Hi everyone, welcome to lecture 8. And in this lecture, we will cover exponential and gamma random variables. So far, we have seen a few random variables and corresponding distribution, and exponential and gamma also one of the important continuous variables and the distributions. So a continuous random variable which can take the non-negative real values with the following PDF is called exponentially distributed. So if that random variable x in this form, so if x is greater than or equal to 0, that is the values x can take, so it should be non-negative. The corresponding PDF, the density, will be lambda times e to the minus lambda times x. Otherwise, that will be 0. So what that means, from minus infinity to 0, the PDF will not be valid, okay? And this is true for some positive constant lambda values, and that is called the rate of the distribution. And you will see in the next slides how the rate of that distribution, how the lambda affects the shape of that distribution, okay? So in order to say that PDF is a proper one, we have to check some properties, right? The first one is that should be non-negative. So let's look at this. Lambda is the positive value, and e to the minus some positive values, because the lambda is positive, x in positive will be the positive, and the results will be positive. So that satisfies the first property. So the second property is accumulating all the densities should be ended up with 1, right? What I mean, if I calculate the density for each possible x values, I have to end up with 1. So how can I do that? If I integrate the PDF for all possible x values from 0 to infinity, the integration of this term should be ended up with 1. So how can I do that? Let's say this guy is u. So let me write here, the minus lambda x is equal to u. That means the minus lambda dx is equal to du. So let's substitute that x's with u. So what will be this guy? That will be lambda times e to the u, times what is the dx? Dx is du divided by minus du divided by lambda. So let's say it is minus, and du divided by lambda. So these two guys will cancel each other, and I will get minus e to the u times du. Okay, but this range from 0 to infinity is valid for the x variable. And let me change it for the u one. So if x is 0, the u will be 0. Okay, the lower limit will not change. And if x is infinity, the u will be minus infinity. Okay, so what will be the new range? This whole things will be the minus integration of e to the u with respect to du from 0 to minus infinity. So because that is a minus sign, I can change this guy as from minus infinity to 0, the e to the u times e to the u with respect to du. So the integration of EU is again EU. So the definite integration will be the e to the u from minus infinity to 0. And if I open this one, it will be e to the u. Sorry, e to the 0 minus e to the minus infinity. So these guys will be 1 minus 0. Okay, e to the minus infinity is 0. So and e to the 0 is 1. So I will end up with 1. So that's mean this PDF is a valid one, so I can use it. Okay. As I say, the lambda is called the rate of the distribution. Okay, so actually the changing the lambda will affect the shape of that exponential distribution. What I mean, let's look at a fib example here, a fib lambda values. The first one is 2, and that corresponds to this distribution. And the second one is 0.5, that corresponds to this one, and 0.1, this one. So no matter the values of lambda, the shape under this curve, the area under this curve will be 1. We just proved that. But the decreasing pace will change, okay? So if you increase the lambda, it will start from respectively high values, high density, but it will decrease sharply. But if you reduce the lambda values, the graph will be more smoother. Okay, it will still decrease, but in a slower pace. So this is how the lambda affect the shape of the distribution. So let's look at the cumulative distribution function, which is the CDF, and how. And remember that why we use the CDF, because if we want to calculate something like that, right, the probability of x will be less than or equal to some value. So to do that, we can integrate the density until some points, some required points, right? The limit will be between 0 to some required point. Let's say that is x, and to avoid the confusion, we change here as t, okay, because x is now the limit of the integration. And let's calculate this one and see what is the CDF of the exponential distribution. First, let's substitute the u with lambda t, okay? And this guy will be the lambda, let me write here, lambda times e to the minus u times. So if u is equal to lambda dt, the du will be equal to lambda times dt. So dt will be du divided by lambda. And that will be du divided by lambda. Okay? And these two guys will cancel each other. And I will end up with e to the minus u times e to the minus u with respect to du. And this limit is for the x value, okay? And in other words, the t value for here. But now I changed the variable, so I have to specify the limits for the new variables. So the t was from 0 to x, right? If I put 0 here, 0 here, the u will start 0 again, okay? And if I put x here, the u will go to the lambda times x. So these will be my new limits. So this term, this u random variable, will go from 0 to lambda times x. Okay, so that is the rewriting of this guy. Okay, let's integrate this term. The integration of this part is simply the minus e to the minus u, and the definite integration will be lambda x and 0. So if I put these values into the u values, that will be the minus e minus e to the minus lambda x minus minus 1. I have minus sign here. So I will end up with 1 minus e to the lambda x, e to the minus lambda x. So this is the CDF of the exponential distribution. Remember that for x is less than 0, the CDF will be 0 because the density is valid only for the positive values or non-negative values. So, so That is the shape of the CDF. Okay, this is the CDF. And or you can see from here, this is the probability graph of exponential distribution, such that the probability of x will be less than or equal to some specific values. So again, the value of lambda will change the shape of the CDF. For example, let's say 1.5. Okay, that corresponds to this CDF. So it will increase more sharper than the other ones, in which the value of the lambda is respectively small. Okay, so this is how the lambda values can change the shape of that distribution. Let's calculate the expected value of exponential distribution. What was that? The expected value of x is the integration of the PDF and the corresponding random variables. Okay, so what I mean, the expected value of x is the integration of x times lambda times e to the minus lambda x dx. So this guy is the PDF actually. Okay, so how we can do that? Actually, we will do the same thing. Let's do that. The u is equal to lambda times x. And this guy, let me write here, from 0 to infinity, the x is u divided by lambda. And I have one lambda here, e to the minus u, and dx will be, if u is equal to lambda times x, du will be lambda times dx, and dx will be the du divided by lambda. So one of these lambdas will cancel each other, and I will end up with this term. That is 1 over lambda times u times e to the minus u du. I can integrate this guy by using the partial integration or integration by parts. So let's say that dv is equal to e minus u du, okay? And remember the partial integration, which is u dv is equal to u times v integration of v times du, okay? So dv is equal to e to the minus u times du, and u is u, and v is, if I take the antiderivative of these guys, I will get the dv, right? So, right? And if I get the antiderivative of this one, I will get the d1. So that will be minus e minus u. Okay? So let's write these things, and it will be more clearer. What I have now, I have this one, and 1 over lambda is a constant, so that can go outside the integration. And inside integration, I will have this one, and I write this one as from 0 to infinity u times dv, okay, u dv. So let's apply this formulation. That will be u times v, that will be minus u times e to the minus u, which is v, and this minus sign is coming from this minus, okay? And minus from 0 to infinity, I'm going to this part, v times v du. What is v? Which is minus e to the minus u and du. Okay, so I just need to calculate this part. Let's continue to calculation. How can I calculate these terms? There's two guys. If u takes the 0, that is easy, it will be 0. But if u takes the infinity, it will be undefined, because if I write this guy as the minus u divided by e to the minus u, that will be minus infinity divided by infinity, that will be undefined. So if this is the case, I can use the L'Hopital rules. What I mean, I can write this guy as this one. The limit u goes to infinity, the eu, and so the limit u goes to infinity, u d. Okay. So derivative of the numerator will be -1, and the derivative of the denominator will be e to the u. Okay. So derivative of the e to the u is equal to e to the u. So this is this is not related with the u, so that will be the -1. Okay. And the denominator, the e to the u, when u goes to the infinity, that will be really large number, right? That will be infinity. So these guys will be -1 divided by infinity, and that will be 0. So we can cancel this first part. Now let's look at the second part. I have the integration of minus e to the minus u du. So these two minus will will end up with plus, and I will have the integration of e to the minus u du. Okay. So what is this one? Remember the PDF of the exponential distribution. These guys, right? Let me write that one, which is lambda times e to the lambda x. If I specify that PDF by taking the lambda values as 1, that will be 1 times e to the minus x, right? So actually, this is same with this one. Instead of x, I just use u. So this is actually the PDF of the exponential distribution, and we found that. What is that? We found that is the one, right? The integration of the PDF for all possible values, we will end up with 1. So these guys will be 1. Oh, sorry, not this one. Sorry, these guys will be 1. Okay, what I have here is 1 over lambda 0 plus 1, and that would be 1 over lambda. Okay, 1 over lambda. So the expected value of exponential distribution is equal to 1 over lambda. So don't worry if you are not comfortable with this parts, that's the calculation steps, don't worry. You just need to remember what is the expected value of exponential distribution, okay, which is 1 over lambda. We will use this information in future problems. Okay, to calculate the variance of the exponential distribution, first calculate the second moment of it. The second moment is the expected value of x squared, and that will be the integration of x squared times lambda times e to the minus lambda x dx from 0 to infinity. And we will apply the same strategy. Let's say u is equal to lambda times x squared. So du will be 2 times lambda times x dx, and dv will be e to the minus lambda x dx. And so the antiderivative of this guy will be the minus 1 over lambda times e to the minus lambda x. Okay, and we can just substitute these new variables. And again, by using the rule of the integration by parts, okay, I will apply this strategy. Again, let me write that one. The integration of q dv, which is equal to u times v minus integration of v times du. Okay. Okay. Well, what is the u, which is the lambda times x squared, and what is the v? The v is minus 1 over lambda times e to the minus lambda x, and the x values range from 0 to infinity, minus the integration of v times du, the integration of v, this is minus 1 over lambda times e to the minus lambda x, this is this guy is v, and du is 2 times lambda x dx. Okay, so I just need to calculate this part. Okay, let's do some cancellation here. These two lambdas will cancel each other, and I will end up with minus x squared times e to the minus lambda x, and plus this plus will come from this 2 minus sign, the multiplication of this 2 sign, and take this 2 over lambda outside of the integration, and I just left 1 over lambda here on purpose, and I will explain why I did in this way. Okay, now let's take this, guys. Okay, we have this guy. Okay, if I can, sorry, let me move this thing here, and let's start from the first part. So if I put 0 into the x, that will be easy. I will end up with 0. But if I put infinite, that will be minus infinite squared times e to the minus lambda infinite. That will be undefined because the results will be minus infinity divided by infinity. That will be undefined. So I can rewrite this part as minus x squared divided by e to the lambda x. Okay, and I can apply the L'Hopital rule. So what it says, I can rewrite this guy as the limit when x goes to the infinity, the minus x squared dx, and the limit x goes to infinity, e to the lambda x dx. Okay, so what is the derivative of this guy? That is minus 2x divided by, what is the derivative of this guy? That is lambda times e to the lambda x, not a minus, e to the lambda x. So now let's put the infinity into the x. That will be 2 times infinity divided by lambda times e to the lambda infinity. That will be the minus infinity divided by infinity. So that will be again undefined. So what I mean, so what I will do, I will reapply the L'Hopital rule. Okay. So I will apply the L'Hopital rule here again. What I mean, I will calculate the limit x goes to infinity, x dx, and divide by the limit x e to the lambda x. So the derivative of this guy will be the -2, and derivative of this guy will be lambda times e to the lambda x. Okay. So this will be the 0, right? Because that will be -2 to infinity, and it will be 0. Okay. So this first part will be equal to 0, and let's look at the second part. This guy 0. What is this one? What is this one? Remember that this lambda times e to the minus lambda x dx is the PDF of the exponential distribution, and x is the corresponding random variables, right? That is actually the CDF, actually the expected value. Let me show it. Look, that one. The expected value of x is equal to integration of x times PDF. So here we have the x times PDF. So what was the expected value of the exponential distribution? Is 1 over p, right? Sorry, 1 over lambda. So this guy is equal to 1 over lambda, and I have 2 over lambda here. That means I will end up with 2 divided by lambda squared. So the second moment of the exponential distribution will be 2 over lambda squared. Well, how can I calculate the variance? It's easy. The variance of x is equal to the second moment minus the square root of the first moment. So expected value of x squared minus expected value of x squared. So it's simply 2 over lambda squared minus 1 over lambda squared. So I will end up with 1 over lambda squared. So the variance of the exponential distribution is 1 over lambda squared. So the expected value of exponential distribution is 1 over lambda, and the variance of the exponential distribution is 1 over lambda squared. So this is end of part 1, and thanks for watching.